Okay, hello everyone. My name is Timothy, and today we're going to be covering the topic of computer architecture, which is classified as a medium topic. So, so let's just get straight into it. So, essentially today we're going to be covering 5 different things. The first thing is about the CPU, the central processing unit. Second one is about the von Neumann architecture. Third one is about the fetch, decode, execute cycle. Fourth one is about the instruction sets, and fifth one is about the embedded systems. And here to the right, meet our companion Fubuki. She's gonna be accompanying us for the entire session. So here's Fubuki, and here's Fubuki as well. Oops, she fell out of my standee. But she's gonna be accompanying us for this entire session, because if I must be blunt, this topic is extremely boring. So, perhaps with an anime girl or an anime a cartoon in here, it can be more fun. So, before we get into the main topic itself, I think it's really important for us to try to change our mindset about hardwares, because when we think of hardwares, we definitely think about very complicated stuff. So, what I usually like to do is that I like to think about hardwares or learning computer architecture as if learning biology. So it's pretty much translating the human body into a computer. So what do I mean? What do I mean by that? So here I have listed down 3 core components which are very similar in a human body and in a computer. The first one is of course the heart. Second one's the brain, and third is the nerves. So the heart allows you to actually live, because the heart pumps blood around your body. It allows you to it allows you to live, and so on. The brain is the one that actually processes everything in your body, and the nerves transfer the signals from your brain into the other body parts, and the other body parts transfer signals to your brain as well. So it's sort of connected to one another. And this also links to computers. It's very similar. So we can think of the heart as a power supply, because without a power supply, a computer can't turn on. The second one is the brain, and the brain, we can think about it as a central processing unit or a CPU. Basically, the CPU is the quote-unquote brain of the computer. Well, we're gonna discuss that later. And then the third one is the nerves, and we can think about this as the buses. And when I say buses here, it doesn't mean like the vehicle bus, but I'm talking about the buses that transfer data from one hardware to another in a PC. So we're going to discuss about that later. Now, let's start off with our first subtopic, which is the CPU, or the central processing unit. So essentially, the CPU is as I said before, the quote-unquote brain of the computer. So it can take in any input and it processes it to give an output. This is basically the one that processes all the instructions in your computer. So if you, let's say, do a specific command such as clicking like this, like what I'm doing right now, that basically gets processed in terms of binary. So it gets sent to the CPU, it processes it, and then it gives an output really quickly. And that output we can see from my monitor, or what you guys are seeing right now in your monitor. So that's what the CPU does. However, since it's processing a lot of things, it gets really, really hot. So that's why we need fans to cool it down. So you can think about it like your human body. So I think I have a meme right here. Yeah, when your fans make a weird noise, so you turn the music up. Computer technician. So essentially, the more information, the more instructions your CPU processes at a given time, the more hot it becomes. You can think about it as your head. The more you think about things, the more hot you feel. So because of that, you need fans to cool it down, because if it gets too hot, then that's bad. Just like when you're when you feel really hot, you're having a fever, you need something cool to cool yourself down, stuff like that. So yeah, that's why the concept of overclocking your PC, so maybe you've overclocked your PC, maybe you've mined Bitcoin or something, that basically essentially overloads your CPU with so much information and instructions that it gets really hot. That's why it can be dangerous in the long term. So that's about CPU. So now there are 3 core components, or 3 key terms, which allow us to define how efficient or effective a CPU is. The first one is the clock speed, second one is the cache or cache, I don't know how to pronounce it, and the third one is the core. So let's start from the clock speed. So basically the clock speed is the number of fetch, decode, execute cycles that can take place in 1 second. We're going to discuss about this later. Essentially, you can say this is the amount of instructions it can do in 1 second, and this is measured in hertz. And essentially, a faster clock speed means more instructions per second, obviously. And if there are more instructions per second, then it's definitely going to be a lot faster, your PC. And this is a fun fact. Modern computers have a clock speed in gigahertz, meaning billion, and a clock speed of 3.5 gigahertz can perform up to 3.5 billion instructions per second. So this is the average clock speed for a CPU at the moment, 3.5 gigahertz. And it can perform this much instructions per second. Just think about the scale of that. That's insane. That's why when I click this mouse right here, it processes it really fast. Like in a split second, it already goes to the next slide, and so on. Yeah, the process is really fast, and that's really cool. Just imagine how small a CPU is, and it can process 3.5 billion instructions per second. That's insane. Next is the cache, and the cache essentially it serves as a temporary storage to provide quick access of a copy of frequently used instructions and data. So essentially, this is the storage system in the CPU itself. And larger cache means more fetch, decode, execute cycles at a time, which means faster performance. Because if you have more storage, you can store in more information, and with more information, you can, process that information more times in a given time. So because of that, it leads to faster performance. And this also correlates with storage. Since cache has a significantly faster read and write speed with RAM than RAM, it makes it much quicker to retrieve instructions from there instead of memory. So if you've learned about RAM, it is a primary storage, and because it's primary, then the computer is able to access the RAM a lot more quickly than, let's say, secondary storage. However, cache here is even faster, because here we're talking about the CPU, right? And the CPU, it needs to process things really fast. That's why this cache serves as the storage of the CPU. It gets the information from the RAM and it stores it in the cache, so that the CPU doesn't need to go back to the RAM. It just needs to go to the cache, so it can process more things at once. So yeah, that's why this cache here exists. Next is the core, and this is essentially the number of CPUs or brains a computer has. So more cores equals more fetch, decode, execute cycles or instructions per second. So yeah, you can think about it like this. So you can see here there's a single core, dual core, and quad core. If in a single core we can process 2 strings of information at a time, in a dual core we can do twice as fast, so 4, and quad core is 8, and so on. So a dual core is 2 times faster, a quad core is 4 times faster, and so on. So that's why more cores is better. Okay, so those are the 3 terms. Now we're going to move on to the second subtopic, which is the von Neumann architecture. Essentially, this is a design of the CPU which has been proposed by mathematician John von Neumann, which is this guy right here, the GOAT. And essentially, what this architecture does is that it outlines how the computer memory, input and output devices, and the processor all work together to process information. So this is the von Neumann architecture right here. Essentially, we can see the input and output devices, and this right here, this big square, is the CPU. So we have the input, it goes to the CPU, it gets processed, and it works with the memory unit, which is the RAM right here, to produce an output. And this output, we can see. So, you might notice we see a lot of things here inside the CPU, such as the control unit, the arithmetic logic unit, and we have a lot of registers here. So we're going to talk about it one at a time. Essentially, these components inside the CPU work together to process information. So let's start with the ALU. So essentially, the ALU here, the arithmetic logic unit, which is this one, it performs arithmetic operations in the CPU. And it also performs logical decisions in the CPU using logic gates. So logic gates such as AND, OR, NOT, NAND, NOR, XOR, and so on. It is all used in the ALU to process these instructions, because you need to remember that these instructions are in the form of binary, zeros and ones. So with this in mind, they can process this information using logic gates, which takes in 2 input, or even 1 for NOT, to produce an output. And then this is essentially how the ALU works, the structure of an ALU. So you might see a lot of terminologies right here, such as operand, opcode, status, integer result, and so on. So let's break it down one by one. First of all is the opcode, which stands for operation code. So this is essentially the operation that needs to be performed. So the opcode is right here, and it enters from the left. Essentially, this is the, let's say, addition, subtraction, multiplication, division, modulus, and so on. It is part of the opcode, which is essentially the symbol. You could think about it like the symbol. So is addition, subtraction, and so on. Meanwhile, the operand is the data that the opcode will use. So the operand is up here. In this case, there are two operands. So let's say we have the operand 1 and 2, and the opcode is plus. So what it does is 1 plus 2 to create the integer result, which is 3. So let me just write that down. So this is, let's say, 1. This is 2. And let's say the opcode here is plus. So the integer result will be 1 plus 2, which is 3. Look at that. So yeah, it is very similar to logic gates. The only exception is that we follow what the opcode tells us to do. And then here there are also statuses, which this is not really important at the moment. This is more complex, but essentially it indicates the outcome of the last operation. So let's say if the last operation it is 0 or it overflows, then that status tweaks this a bit to adapt to the previous outcome. You don't need to think about it too much. It's not too important at the moment. What is important is this concept, operand and opcodes. And the integer result is pretty much the output. Okay. Next is the control unit. And control unit is this one right here. And this essentially coordinates how data moves around the CPU by sending the signal to control the movement of the data. So if you see here, the control unit is right here. And then it controls this is IO is input output, IO units, the memory, and the ALU. So essentially it is able to control what data goes in and out and when it goes in and out. So let's say if the ALU is processing something at the moment, then it sort of cuts off anything from the input output and the memory, because it's processing something at the moment. If something else goes inside, then it's gonna ruin everything. It's gonna overload the ALU. And it essentially also decodes the instructions fetched from memory, because the instructions from memory and the instructions processed in the ALU are two completely different languages. In the ALU, it requires binary. In memory, it's something else. So that's why the control unit needs, it acts as a translator to translate the things from memory to the ALU. And this also correlates to the fetch, decode, execute cycle, where this is the decode step. So we're gonna talk about that more later. So yeah, that is the control unit. Let's move on. So now this is where it gets a bit complicated. So these are registers. They are extremely small and extremely fast memory located in the CPU, and it holds small amount of data needed as part of the fetch, decode. Did I forget the decode? Fetch, decode, execute. Sorry about that. Cycle. And then there are 5 main registers, which are the program counter, the memory address register, memory data register, accumulator, and current instruction register. And these can be abbreviated as these. So PC, MAR, MDR, ACC, and TIR. So we're gonna talk about this more later. It is, I admit, a bit vague, the explanation here, but it will all make sense after we get to the fetch, decode, execute cycle, the functions of each of these registers. So now, what are buses? As I said before, buses are a set of parallel wires through which data is transmitted from one component to another. So yeah, it is basically the transfer of information, data from one part of the hardware to another. So there are 3 types of buses. The first one is the address bus, the second one is the data bus, and the third one is the control bus. So the address bus, as per its name, carries the address. The data carries the data or instructions, and basically the control bus carries commands and control signals to tell components when they should be receiving reads or writes. So this correlates again to the control unit, where sometimes they block data transfer because something is going on, and if you continue pumping them with data, it gets overflowed. So that's why there's the control bus, which essentially sends the command to tell other components to, hey, stop first, because things are going on at the moment, so don't send data yet, and so on, stuff like that. So yeah, these are the concepts of buses. So there are, control bus, address bus, and data bus. There's a CPU, memory, and input and output. This memory again is the RAM. So they're the same thing. Don't get confused. So essentially, the address bus is unidirectional, and uni in this case means 1. The data and control bus is bidirectional, and bi here means 2. So what does this mean? So if we see the address bus right here, we see this part, and we see the arrows which connect to it. You see this one and this one. They all go only in one direction. So in this case, from the CPU to the address bus, it goes only one direction. And from the address bus to the input and output devices, it only goes one direction. Meanwhile, in the data and control bus, it is in 2 directions. So as you can see here, the rest, it's all 2 directions. And this essentially tells us the flow of where the data is going. So the data from the CPU to the address bus, it can only go in this flow. It can only go from CPU to address bus. It can't go from the address bus to the CPU. And this also applies for the input and output and address bus. Meanwhile, for the bidirectional ones, it can go in 2 directions. So it can transfer data to one another, as so. So yeah, that is the concept of it. You don't need to get too confused about it at the moment. Let's go next first. Now here is where it gets a bit complicated and very boring and very memorizing heavy, and even I hate this topic, but we have to get through it together. So this is the fetch, decode, execute cycle. It is the fundamental process by which a CPU retrieves instructions from memory, decodes them, and executes them. And the sequence of operations that allows a computer to execute programs and perform tasks is this, the fetch, decode, execute cycle. So we have the control, we start from the RAM here. Oh my god, what is that marker? That is very big. We start from the RAM, which fetches information, and then it gets processed. It goes to the registers first. It gets stored here, and then it gets decoded by the control unit. As I said before, the control unit decodes, information, and then it gets executed in the ALU, and then it goes back to the RAM, essentially. That's the TLDR of it. But it gets a lot more complicated right here. Okay, this is the diagram which illustrates the fetch, decode, execute cycle. And yeah, that is a lot of stuff. Like, you can see Fubuki here. So desu ne. It is a lot to take in. So let's break it down one by one. Okay, so first of all, let's try to identify the components here first. So we have the CPU and the RAM and the buses right here. So these 3 are core to the fetch, decode, execute cycle. Okay, so first of all, let's begin with the input. So the input here is part of the RAM. So the RAM, it's a storage device. So it stores the input from the input device, and then it gets sent to the control bus. So essentially what it's saying is that, yo, CPU, I got an input right here. So can you please process it? And they're like, okay. So it gets sent along the control bus, and then it goes to the control unit in the CPU. So let's say the input right here, the input is always in the form of an address. That's one thing. So let's say the input is 00000001. Okay, let's say the input is that. Let me just write it down here so we don't forget. So it's 00000001. So it goes to the control unit, and then the program counter copies that. So it's, okay, the address is 00000001. Got it. And then the MAR also copies that. So it's like, oh, okay, so it's 00000001. The reason why the MAR copies that is because it's the one that can communicate with the RAM. So after the MAR gets the address, the MAR sends a request to the RAM to retrieve the corresponding data. So it's like, RAM, yo, I got this address right here. I got 00000001. can you send me the data that corresponds to the address? And then the RAM's like, oh, okay, sure. So the data right here is 0001111. I'll send it back to you. And you have to consider that the address bus is unidirectional, so it cannot go back to the CU using the address bus. It needs to go through the data bus. That's why it's called data. So it goes back, and then it goes to the MDR right here. So it stores that data. So it's like, okay, here's the data 0001111, as so. And then after that, this MDR copies, the CIR copies the data from the MDR. So the CIR puts in 0001111. And then after that, the program counter increments its value by 1. So what I mean by increment is that it's binary addition. So let's say 00000001, and then we add it by 1. So what does that become? So it becomes this. You should learn it. You should have learned it in the previous lesson. It becomes 00000010, and this is the address of the next data. So essentially, the PC is preparing itself for the next set of instructions, so it's more efficient later. So the process repeats automatically. It doesn't have to, wait for the control bus to send another signal. The PC immediately gets the address for the MAR to copy for the next instruction. Essentially like that. Okay. Now, going back to the CIR sends this data to the ALU. Now, this data right here, the 0001111, contains both opcodes and operand. So, it contains opcode and operand. Okay, and as I said before, this code is essentially the symbol. So let's say addition, subtraction, multiplication, division, and so on. And the AND here is the input data. So it has both things, and then it gets sent to the ALU. And this ALU here does the process. So as I did before, 1 plus 2 is 3. That's done in the ALU. And after that's done, the result goes to both the accumulator and the general purpose registers, which are both essentially storage devices in the CPU. And then the process rinses and repeat. So yeah, that is essentially how the fetch, decode, execute cycle works. The process repeats next with the PC, which has already incremented the address, copying to the MAR. So the MAR now changed its value to 0000010, and then it sends a signal to here, so it the RAM, and then it fetches it, and then it goes to the data, and then the data gets sent again through the address bus to the MDR, and then it changes it, and so on. It rinses and repeats. So the fetch, decode, execute cycle, that's why it's called a cycle. It repeats the same thing over and over again. So it processes one information at a time, each data at a time, each address at a time. So that's why a modern computer, as I said before, has 3.5 gigahertz. It needs to process 3.5 billion instructions at a time. It's because the process is so repetitive and so slow. So you really need that clock speed. You really need that core, that cache, so it can process all of this at a time. So that's essentially how the fetch, decode, execute cycle works. If you want to review yourself, you can read through this. This is essentially the purpose of each register, as I've said before, as explained in the diagram. So essentially, the program counter temporarily stores the address location of the next instruction to be carried out and increments the address by 1. The MAR, it stores the address, the MDR stores the data, the CIR as well, and the accumulator stores the results from the ALU temporarily. So that's for the registers. This is the fetch, decode, execute cycle. Nothing too much here. So fetching is essentially the process of fetching the information using the address and data and so on. Decode here, I forgot to mention the decode. I apologize for that. So the decode happens in the control unit, as I've explained previously. So before it gets sent to the ALU, the data in the CIR is decoded first. And then, and then finally execute is essentially in the ALU, where it executes the operation and returns the desired results. And then these are two frequently asked questions regarding this topic. So first of all, why do both the PC and MER store the same thing temporarily? So essentially, if you remember, the PC, first of all, stores the address, let's say this one, so 00000000, and the MER copies from the PC and stores the same thing. Why is that? Why doesn't the MER store it directly instead of storing at the PC? And that's because essentially the PC here serves as what's the name? It serves it keeps track of where to go next, and the MER tells the memory this is the location I want now. So this PC is basically preparing for the future. The MER is telling the memory the address now. Since, as I said before, the PC here will increment as soon as the data has been obtained by the MDR and the CIR. So as it increments, and then this process LU to accumulator and so on finishes, the calculation finishes, it immediately processes the next address. It doesn't need to go back to the control bus and then obtain the input again from the RAM and so on. It can just look at the PC. So the MER can just copy the PC directly. So it is more efficient that way. Second of all, why do both the MDR and CIR store the same thing? So again, if you notice, after we obtain the data, so let's say this one, the MDR stores 0111000, and the CIR also stores 0111000. Why is that? And this is because it ensures that the current instruction is kept safe so that the MDR can be used during the execute stage to store additional data that is needed. So when the ALU starts processing and does calculations, sometimes it needs extra memory or another storage device to help store some calculations. And if that's the case, then it uses the MDR. But then, if the MDR's data is erased and removed, then how does the ALU still keep track of the current information? And that's where the CIR comes in. So it reads from the CIR. It does not read from the MDR. The MDR serves as, the additional storage. That's why they both have the same information. So let's breathe first. That was a lot. Jeez, that is a lot. This is why CS majors absolutely hate circuits, CPUs, embedded systems, and so on. It scares us. I hate it a lot. So yeah, let's breathe first. The rest should be easy peasy lemon squeezy. It's not a lot left. So next up is instruction sets, which is essentially a list of all the commands that can be processed by CPU. And one thing to note is that a program created using one computer's instruction set would not run on a computer containing a processor made by a different manufacturer. So for example, a computer program that is created using Intel's instruction set would not run on a device containing an ARM processor. Since they're both from different manufacturers, it cannot be processed by the ARM. Why? Because here's an example of an instruction set. So let's say we have this instruction set, which is for adding numbers. So yeah, this is an instruction set, this singular thing right here. So the purpose of this instruction set is to add values. Add the contents of register A to that of the accumulator. So an instruction set has the binary as well as the opcode. So this is the opcode. Essentially, it is a code which represents the instruction set. And this is also the binary version of said instruction set. So the reason why it cannot be used on a processor of a different manufacturer is because the opcode and the binary might be different. And therefore, they can jumble it up, or it might not even be defined for said processor. a different processor might read it and be like, this is not, I can't find this in my own instruction set. They get confused. That's why the instruction set and the processor has to come from the same manufacturer, because the binary and the opcodes matches for one another. So that is an instruction set. Next up, and finally, is the embedded systems. And these are specific and specialized computer systems designed to perform dedicated functions within a larger system. And this typically includes a microprocessor, memory, input and output devices, and software that runs in a loop. So essentially, it is a system inside a system. So for example, we have a washing machine. So this washing machine here is the main system, the main device. However, inside the washing machine itself, there is a program to control the wash cycle, how long one wash cycle is. So it is a smaller system inside a bigger system. Another example is a fridge, a refrigerator. So, the whole system here, the whole device is the fridge. However, inside the fridge itself, there is a smaller system to maintain the temperature and also controls it using logic gates, like that. Another one is ATM. So the main system is the ATM. The small system is algorithms which help dispense the cash and to verify the PIN, stuff like that. So yeah, those are what embedded systems are. They are basically systems inside a larger system. And there are many examples of these in our day-to-day life. You can find them anywhere around you these days. So yeah, those are embedded systems. Okay, so that concludes it for today's session. So have some Fubukis. Yeah, Fubukis. She's happy. Yeah, this is definitely a lot to take in. This topic is very memorization heavy. So I would highly suggest you guys tackle this topic one step at a time. I would definitely recommend, don't memorize all of this, okay? Like these jumbles of text, don't memorize it. Each word, each line, don't memorize it. Try to fully understand and grasp this diagram right here. This diagram, if you're able to, follow through the arrows and you're able to fully understand the logic behind how the cycle, can process information, then you guys are set. Okay, there's a clear difference, a clear line between memorizing these jumble of text and trying to fully understand this diagram right here. If you're able to understand it, then you're able to memorize it. If you memorize this, you may not be able to understand the diagram. That's the thing. And then if you're able to memorize this diagram, you should be able to do everything else here, because this concept of unidirectional and bidirectional should be clear if you memorize this diagram, if you fully understand this diagram, since you're able to understand where each data, each address, each instruction goes from one part of the computer to another, and so on. You will have to memorize the registers though. That's one thing that kind of sucks. And as well as the buses as well. So you will have to memorize that, unfortunately. But more or less, that is the whole entire topic for computer architecture. So yeah, so I thank you all for listening. Happy learning. Please don't stress out because this topic's kind of heavy. Don't stress yourself out. And yeah, thank you for watching and see you in the next lesson.